Hello and welcome to another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson number 9 on partitioning a line segment. Now I can kind of give you a sense for what this is all about. Partitioning, right, that word, means to break something up, to divide it up into component parts. So what we're going to be doing today is actually very simple. It's going to be kind of the same problem again and again and again. I'm just going to be putting little spins on it, if you will. We're going to be taking a line segment in the coordinate plane, so we're going to know its endpoints in the coordinate plane, and we're going to be breaking it up into two other line segments where the ratios of their lengths are given to us. That's basically it. We're partitioning a line segment, breaking it up into segments whose lengths have a particular ratio with one another. And given that this unit is all about ratios, well, then that kind of makes some sense. So let's jump into it. All right, partitioning, to divide a geometric object up into parts. And in order to do this, we're going to subtly use the side splitter theorem, yes, the side splitter theorem, from the last lesson. Now remember, the side splitter theorem says that a line parallel to a given side of a triangle will partition the other two sides proportionally. And we're going to take some subtle advantage of that today with partitioning problems. So let's kind of get into it in our first exercise. Take a look at a very special type of partitioning. Exercise number 1. Segment AB lies in the coordinate plane with point P on segment AB such that AP to PB equals 1 to 1. AP to PB equals 1 to 1. If the endpoints are at A, -213, and B, 8, 5, then answer the following questions. All right. So again, it's important that you understand this symbolism. You've been seeing ratios written with that colon notation. All right, we could have also written it as something like this. AP over PB is equal to 1 over 1. All right. But most often we're going to see those ratios written in the colon form like that. So I'm going to get rid of this. All right, now, letter A. What can you say based on the givens about the lengths of AP and PB? Draw a picture to help. All right, think about this for a minute. Pause the video and tell me what you can say about AP and PB, their lengths, that is. Well, they have to be the same length. You know, the idea of a ratio of 1 to 1 really means that one part of AP equals one part of PB. All right, 1 to 1. And in fact, the idea is, if we do have that picture, right, that these two have to be the same length. Now, they certainly don't, AP equals BP. They certainly do not need to both be a length of 1. All right, actually, let me write that a little bit better. All right, they don't need to be a length of 1. They just have to be the same length. So in other words, this could be 5 and this could be 5 because 5 to 5 is the same as 1 to 1. Right? 1 to 1 means that they're equal to each other. They could both be 15, right? 15 to 15 equals 1 to 1, all right? And they aren't a length of 1. We could certainly figure that out using the distance formula, but we're not going to, okay? They just have to be the same length, that's all. You know, again, I'll leave them as lengths of 5, even though they certainly aren't and don't need to be. But now let's take a look at letter B. Letter B says, what special point is P on line segment AB? Find the coordinates of P. Okay. Pause the video now and see if you can figure that out. Right? What special point is P and what are its coordinates? All right. Well, if P divides AB into two segments of equal length, then there's only one name for it. P is the midpoint of AB. And of course I can find its coordinates very easily by using the midpoint formula, which would say that I will take the average of the x-coordinates, -2 plus 8 divided by 2, and the average of the y-coordinates, 13 plus 5 divided by 2. All right, that's going to give me 6 divided by 2, and 18 divided by 2, and that's going to give me P at 3, 9. All right, so simple. But of course, P, or the midpoint, is a very special partitioning of a line segment, right? It's simply cutting it into two equal segments, hence giving us that ratio of 1 to 1. All right, what we want to now do is, given a line segment that has endpoints given in the coordinate plane and some ratio given, right, to locate the point P that divides the line segment into those proportions. Now, side note, this is a very specific standard in the Common Core geometry standards, which is almost always tested on standardized exams. So even though this is kind of a very routine problem, it's certainly something that you want to learn how to do, and learn how to do well. So let's take a look at our first real problem. All right, in this situation, let's take a look at exercise 2. In the following graph, segment AB has endpoints at A, 0, 10, and B, 15, 0. We want to locate point P on AB such that AP to PB is 3 to 2. Okay, and again, so that you understand this, the idea is that wherever P is located, the length of AP and the length of PB are always in a ratio of 6 to 2. That could be that AP is, 3 to 2. That could be that AP is 3 and PB is 2. It could be that AP is 6 and PB is 4. Or it could be 9 and 6, right? It can be a variety of different ratios that when reduced become 3 to 2. So the question is, how do we find point P without getting really messy with the distance formula? You could conceivably do this using the distance formula, but given that that involves square roots and squaring and all sorts of things, I don't think we want to go there yet. So let me walk you through how to do it. Letter A. Draw triangle AOB without the grid and mark the approximate, not the appropriate, but the approximate location of P on AB. All right, so let's do this. Let's take this triangle. I'm even gonna put a little right angle here because this is certainly a right triangle. And what do I know? Well, wherever P is, the length of AP is longer than the length of BP or PB, either way. So maybe I'll put it like right around here. Okay, and remember, that length to that length is 3 to 2. So that's it, that's all I want. We're going to come back to this diagram though in just a little bit. Letter B, on your diagram above, draw a vertical line from P down to side OB. All right, that's easy enough. Vertical line. Mark the intersection C. Cool, I can do that. Why must PC be parallel to OA, right? Why do those two have to be parallel? Make sure you can answer that question. All right, let's do it. PC is parallel to OA because they are both vertical. Right? They're both vertical lines. And all vertical lines are parallel to each other, as are all horizontal lines. Right? They're both parallel lines. And this is now where the side splitter theorem is going to come in. Because remember, when we have two lines that are parallel, as these two are, then it splits the sides of the triangle proportionally. So AP to PB will have to be OC to CB. The ratio of AP to PB, which we know is 3 to 2, must be the same as the ratio of OC to OB. Woohoo! So what is the ratio of OC to CB? Question mark, explain, then algebraically find the coordinates of C. All right, so I kind of gave this away, but OC to CB must be 3 to 2 because of the side splitter theorem. Right? Because of the side splitter theorem. Now, notice now, I want to know where C is. Okay, I'm not yet worried about where P is. I'm worried about where C is. So how do I find that? Well, this goes back to a technique that we learned in the lesson on the side splitter theorem. All right, I know that the ratio of OC to CB is 3 to 2 because I know that the ratio of AP to PB is 3 to 2. So what I'm going to do is I'm going to let OC, I'm going to write it right on here, I'm going to let this be equal to 3x. And I'm going to let this be equal to 2x. And the beautiful thing about OB, right, is that it's a horizontal line. So I can literally look at OB, right, and I know the length of OB, maybe I'll write it right up here, the length of OB is 15, right? We can see it right there. It's 15 units long, right? That's the x-coordinate of B, it's 15 units long. So what I can now do, let me extend my page a little bit, is I can now say, well, I've got 3x plus 2x is equal to 15. So that gives me 5x is equal to 15, and x is equal to 3. Now, well, what can I do with that? Right? Well, x is equal to 3, right? So this distance, 3x, must be equal to 9. And that means that the coordinates of C, right, are at 9, 0. Now, the 0 is just the fact that the C is somewhere along here, right? So I can actually mark it right on my diagram. There it is. There's my C, okay? And what it's really done is it's broken this into 9 and 6, right? This has got a length of 9, and this has got a length of 6, all right? And now here's the beautiful thing. Where is P? Well, P must be right here. Remember, P was just vertically above C, so I can just read the coordinates off, right? P now has coordinates exactly the same as C, 9, but then at a y-coordinate of 4, okay? And at the end of the day, I actually don't know what these two lengths are. I don't know what those two lengths are. I don't. To figure out those two lengths, I'd actually have to go ahead and use the distance formula or the Pythagorean theorem to figure out the length of AB, right? And then I could use the length of AB to sort of figure out the lengths of those two segments, or I could use point P and the distance formula to find AP and PB. But I don't need to, because by figuring out the coordinates of C, I was able to figure out the coordinates of P. And again, the reason that I did it this way is because it was easy to deal with this horizontal line segment, all right? Now let's be clear about this. I had some advantages here. I had this line segment, I had a piece of graph paper, you don't always have that, and we're going to get into all those different scenarios in a moment. But regardless, we will always be taking a line segment that's slanted, okay? And we'll be taking that ratio, like 3 to 2, and breaking up either the horizontal or, either the vertical or the horizontal segments, and using those to locate the point on the slanted segment. So let's kind of keep going with this. All right, a little bit more challenging. And the reason that this one's going to be more challenging is that before, the two endpoints were on the axes. Now they're just kind of hanging out. Let's take a look at the problem. Exercise number 3. On the grid to the right, EF is plotted with endpoints at -6, -4, and 8, 3. We want to find the coordinates of point G lying on EF such that EG to GF is 3 to 4. Letter A, draw a right triangle below with EF as the hypotenuse and the horizontal and vertical legs. Label the lengths of these legs. All right, so let's do it. All right, let's go like this. This is E, this is F. Let's draw in a right triangle. All right, and I'd like you to take a moment and figure out what the lengths of those two legs are. Don't worry about the length of the hypotenuse. All right, well, it's pretty easy. You know, you can just do it by subtraction. You can say, well, 8 minus -6 is 14. Right? You can always find the distance between two coordinate points by doing subtraction. 8 minus -6 is 14, and 3 minus -4 is 7. Okay? So I've got one leg that's 14, and I've got one leg that's 7. All right? Now, let's keep going. Letter B, find the coordinates of G. Show how you would arrive at your answer. All right, well, let's first kind of locate, like we did before, G, a little bit, kind of an approximate location here. EG to GF is 3 to 4, so EG is slightly smaller. All right, and what we know is the ratio of EG to GF is 3 to 4. This is not a length of 7, okay? So it's not a length of 3 and a length of 4. It's probably pretty ugly lengths involving radicals and things like that, but their ratio is 3 to 4. Now, what that allows me to do, though, is draw this vertical line down like this, okay? Now again, that's going to be parallel to that one, okay? And I can now call this 3x and 4x. Maybe I'll redraw this picture down here. Oh, actually, it's just fine like that, although this is extremely messy. Maybe lower my 14. Whoop, that didn't work. That just made things all the worse. There. All right. Not great. The 3x and the 4x are what are problematic. Let me kind of get rid of those a bit. Okay. So what I've got, I'll put them in here, 3x and 4x. Okay? So what I'm going to do now is I'm going to go 3x plus 4x is equal to 14. All right, I'm trying to figure out those two horizontal line segments. So I'll get 7x is equal to 14 and x is equal to 2. All right? That means in reality what I really have is I really have the following. I've got G, I've got E, and I've got F. All right? And this has to have a length of 6, and this has to have a length of 8. Right? The 6 and the 8. Now, what do I do with that? Well, I know point E has coordinates at -6, -4. All right, so where is this point? Whatever I call it, right, that point is going to be 6 units to the right of this point. I don't know, you know, and then it's going to have a y coordinate that's at E, but it's going to be 6 units to the right. Notice that that's got an x coordinate at -6, so the x coordinate of this point is x equals 0. But that means that's also the x coordinate of point G. Now, we've got the graph paper here, so literally I can just come in and I know that must be G, because that's the only point on my line segment that has an x coordinate of 0. And again, the way I got the x coordinate of 0 is by knowing that E had an x coordinate of -6, by knowing that the horizontal distance G was away from E was 6 units. So if I go 6 units to the right of -6, I'm at an x coordinate of 0. What's the y coordinate? Well, that I can read directly off the graph, and that gives me the coordinate point. Okay? That's the whole deal. It was very, very easy, using that ratio, to figure out how the horizontal portion of this right triangle was partitioned. Then I can use the side splitter theorem to say, well, that's got to be the same way that the hypotenuse, which is really what I care about, gets partitioned. Using that, we can set up an equation, solve, and figure out what the x-coordinate of our point G is, not P this time, but point G, and then just from the graph, we can read off the y-coordinate. All right, let me pause for a little bit, get out of the way, take a look at this, write down anything you have to, process it a bit, think about it. Okay, let's keep going. Now, no grid, no problem. Maybe a little more of a problem. So what was huge in both the last two problems is that we had the line segment and we had it plotted on a grid, right? So we just had to find that x-coordinate, go to our graph, read the y-coordinate off. Let's take a look at one where we don't have graph paper, because that could happen to you. Here we go. Exercise number 4. Segment CD has point E located on it such that CE to ED is 3 to 5. If the endpoints are located at -5, -6, and 11, 18, then find the coordinates of E. Show how you arrived at your answer. Whew. All right. No grid, okay? But we're still going to do essentially the same thing, all right? So what I'd like you to do is pause the video, do a little sketch, draw out that right triangle, do whatever partitioning you can, and then we're going to take a look at it. Okay, but take a few minutes to see how far you can get. And if you think you can get all the way to the coordinates of E, please do. All right, let's go through it. So here we go. C, and we'll kind of do this, D. All right, draw in my right triangle. All right, got my nice mouse pointer. That didn't work. There, maybe that's better, probably not. Okay, now I want to label my right triangle. Okay, so how long is this? Well, again, if I think about it, I'm starting at an x-coordinate of -5, and I'm going to an x-coordinate of 11, so that's 16 units. Then if I want to label this, I'm starting at a y-coordinate of -6, and I'm going up to a y-coordinate of 18, that's 24 units. Make sure that you understand that. If you don't, pause for a minute and just think about it. I'd have to travel 6 units to just go from -6 up to 0, then I'd have to travel another 18 units for a total of 24. Okay, so far so good. Now where is E? E is located on here so that CE to ED is 3 to 5. So maybe I'll put an E right like that. And what I know is that will break this into 3x and 5x. And now I can do that little equation work I did before. 3x plus 5x is equal to 16. 8x is equal to 16. And x is equal to 2. All right? So far so good. So what does that mean? That means that this is going to be, what, 6, and this is going to be 10, right? 6 and 10. Now, what that will allow me to do is figure out the x-coordinate of E, right? So here we've got C, and it's at -5, -6. And if I go then 6 units to the right of it, then E will have a y-coordinate, an x-coordinate of 1, right? If I'm at -5 and I go 6 units to the right, I'm now at an x-coordinate of 1. But what's trickier in this problem than the previous problems is once I had in the previous problems that x-coordinate, I'd just look at my graph and I'd pull the y-coordinate right off. And if you're given graph paper in this situation, or you can have a piece of graph paper, I would still suggest that. But let's pretend we don't have that. How can we now figure out the y-coordinate? We can do that by doing exactly the same thing that we just did, except in the vertical direction. All right? And here's what I mean. What I'm going to do now is I'm going to draw this in. Now remember, it's 3 to 5, 3 to 5, 3 to 5. And I'm going to choose a different letter. I'm not going to use x anymore. I'm going to use y. So I'm going to say 3y and 5y. Okay? And then I'm going to do the same kind of idea. I'm going to say 3y plus 5y is equal to 24. That's going to give me 8y is equal to 24, and y is equal to 3. All right, that allows me to now say that this is 9, and this is 15. That doesn't look like a very good 15. Let me rewrite it so that you can see it on your video better. This is 15. Now the beautiful thing is, that means that the y-coordinate of E is either 15 units below D, or 9 units above C. Either way. Let's go just with C. So C starts at -6, right? And if I go 9 units up from -6, I'll be at +3. Now, one thing that's a really nice check on that is it's also 15 units below D. So since D has a y-coordinate at 18, if you go 15 below that, you're also at a value of 3. Right? So the coordinates of E are 1, 3. We could have also done that same check, right, if we had come over to D and we had subtracted 10 units off of its x-coordinate, right? Its x-coordinate is at 11. Whoops, that's not erasing. There, it's erasing. Right? If we took our D and we subtracted off this 10 units from its x-coordinate, that would put us at an x-coordinate of 1. All right? So without a grid, probably the most effective thing to do is sort of partitioning both the horizontal and the vertical and using them both to figure out the new coordinates of that point. All right, let me step back, give you a moment to copy down anything you need to, and then we'll do one last problem. All right, let's do it. So here we go. Last problem, little multiple choice problem, little spin on what we've been doing. Let's take a look. Segment EF has endpoints at -7, 14 and 11, 5. Point P lies on EF at -3, 12. Which of the following is the ratio of EP to PF? EP to PF. All right, now not that it matters that much, but if I want to draw a little sketch of this, notice that, yeah, we're going from -7 to 11, so that's getting larger, but we're going from 14 down to 5, so that's actually decreasing. So my picture really, if I really kind of wanted to get into it, E at -7, 14, and F at 11, 5, right? Kind of looks like that. And they tell me that P lies on here at -3, 12. I don't know, maybe right here. So P at -3, 12. Again, I'm assuming that we don't have graph paper on this. So there we go. And now what it wants to know is the ratio of EP to PF. Now look, one way to do this, sort of, if you will, the long way of doing this, is use the distance formula to calculate that length, use the distance formula to calculate that length, and then figure out the ratio. That's completely fine. I will say it's likely to get a little bit messy. There would definitely be radicals involved in this particular problem, maybe not in every problem, but in this particular one. But look at how easy we can do it if we consider that partitioning idea again, the side splitter theorem, right? One thing I know for certain is that this horizontal length to go from -7 to 11, right, think about this, is 18 units, right? It's 18 units. Now, on the other hand, to go from -7 to 3, that's 4 units, and to go from -3 to 11, that's 14 units, right? Just think about it. -7 to -3, only horizontal, is 4 units. -3 to 11 is 14 units. Right? And of course they both add up to be that 18, which I don't actually need. Because now, if I want to know the ratio of EP to PF, well, that's got to be, by the side splitter theorem, 4 to 14. And of course the ratio of 4 to 14 is the same as the ratio of 2 to 7. All right? Again, what we're using every time in every one of these problems is the side splitter theorem. And we're either doing the side splitter theorem with vertical lines, or in that case where we didn't have grids, both vertical and horizontal lines. The reason this is so effective is in the coordinate grid, horizontal and vertical distances can always be calculated by simply subtracting coordinates. There's no distance formula that you need. You should be able to look at this and say, yep, the horizontal distance between -7 and 11 is 18 units. And between -7 and -3 is 4, and between -3 and 11 is 14, right? Slanted line segments in the coordinate plane, those lengths you have to do using the distance formula or the Pythagorean theorem, which makes them way harder and way more messy, all right? But the side splitter theorem says, hey, just deal with the horizontal and the vertical, and then use those ratios to help you figure out what's going along the slanted line. All right, let's wrap it up. Although really, that kind of was the wrap up. What we saw today was the primary application of the side splitter theorem, which is if you take a line segment, especially a slanted line segment in the coordinate plane, and you want to partition it with a point that lies somewhere on it in a particular ratio, then you can do that by actually just kind of constructing a right triangle and partitioning the horizontal and the vertical legs of the right triangle given that ratio. Because, again, the ratio of the lengths of that hypotenuse, that slanted leg segment, will be the same as the ratios of the lengths of those horizontal and vertical segments. Side splitter theorem. All right, great. For now though, I'd like to thank you for joining me for another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.